Hello there, this is me Face. I'm going to try and do something different today, a programming tutorial. Well, in the beginning, this channel was supposed to be about programming, audio programming specifically, but things took a rather different turn. For the better, I hope. I really wanted to get the basics down and build the foundations before tackling some of the more challenging issues. So anyway, in the last video, I talked about containers and file formats. And I gave a general overview of it by taking the example of a WAV file format. This video is going to complement that. So we're going to programmatically create a WAV file from scratch. This would include a little bit of audio in it as well. This might look like a scary problem to tackle, but as you'll soon find out, it's not too hard. For the audio itself, we'll just keep it simple. Just a simple sine wave with a fixed frequency and a constant duration. We'll focus more on the specifications of the WAV file format. You can write this in any language you want to. Java, JavaScript, Go, Python, whatever you want. The syntax might differ a little, but the concepts will remain the same. I am going to choose to write in C++ because let's get started. So this is a simple hello world program right now. I'm running on Windows with the MinGW compiler, and I'm using the Cline IDE from JetBrains. This is going to be a simple program contained within a single file, so I don't need to configure a makefile or anything like that for this. The first thing we're going to do is figure out the audio that goes into the file. A simple sine wave. For this we need a simple sine wave oscillator. So I'll start by creating a sine oscillator class. What will need to go into this class? For starters, we need some internal variables to hold the state of this oscillator. A couple of obvious ones that I can think of would be the frequency and the amplitude of the sine wave that would need to be generated. So I'll create a couple of member variables to hold these two variables. I'll create a public constructor for this class. The first argument that it would accept is the frequency and then the amplitude. And I'll initialize these two variables using the member list initializers. We'll expose one method in this class which will generate the next sample value when called. We'll call this process. This is going to hold the bulk of the logic for the sine wave oscillator. And for this, you'll need a little bit of theory. You can check out the module on the origins of the sine wave that I've done to fully comprehend sinusoids and how this formula is derived. But I'll give you a quick rundown over here. So here's a simulation of the sine wave over time, or the x-axis here. The formula is a sine 2 pi fx plus phi. A is the amplitude, which determines the amplitude of the sine wave. In our case, we want to constrain this value from positive 1 to negative 1. So the result of the sine function, when a is set to 1, is that it'll swing from positive 1 to negative 1 over and over again, since it's a periodic function. 2 pi is a constant, and we can leave it as it is. F is the frequency, and as you can imagine, that would affect the frequency of the sine wave. And phi is the phase offset. We can just leave it at 0 for now. We don't have to complicate it. So the simplified formula would be a sine 2 pi f x. X here is the x-axis, but in the analog domain, it would be the time axis. We calculate the sine function over time. But since we're dealing with digital sine waves here, we have to generate discrete signals. So we have to think about it not in terms of time, but in terms of the samples, or the number of samples, or the sampling interval. So if we take a sample rate of 44.1 kilohertz, for example, each second would be made up of 44,100 different samples. If we were to generate a 1 Hz sine wave, this sine function would have to complete its period at every 44,100th sampling interval. Something like this. The frequency aspect of it would remain the same. As you vary the frequency, you can determine how many periods of the sine function are present within the 44,100 sampling intervals. The only thing that's changed is our perception of how we look at sine waves. Instead of varying them over time, we vary them over the sample intervals. Let's try and implement this. The process function would need to be called every sampling interval. So this function would need to be fast because it would need to be called a lot of times. Let's return a floating point value from it. And we'll implement this formula, a sine 2 pi f by sampling rate. For that, return amplitude times sine. Now, the sine function is present within the CMath header file, so we'll include that there. The angle to the sine function will be 2 times pi. Well, you can use 3.14, but if you want more precision, you can use the m pi constant, which is defined within the CMath header. So that will be 3.141592 and so on. 2 times pi times frequency divided by the sample rate. Now the sample rate is 44,100 in our example, but we can define it as a global constant because we might need to use it elsewhere in our example here, in our program. I'll reference that here. Well, it's not really done yet because this function here would return, well, the exact same value every time because nothing is changing here. The angle to the sine function remains constant throughout. So we need some way to offset this value every time we call it. We can consider this the angle to the sine function, and so we need to update the angle every time this method is called. We need to save this angle as a state variable. So we'll call it angle and start from 0. We can capture the value of the sample here. And then we can increment the value of the angle and then return the sample. So angle would then be incremented by this amount. And then we'll return the sample value. Over here, the angle to the sine function starts from 0 and over time will grow. Well, we don't have to constrain the boundary of the angle. Even if it grows quite large, it will round back to 0 at some point of time. So we don't really have to worry about it, especially in our case where we wouldn't be generating quite a lot of audio. There is room for optimization here because the angle increment would need to be calculated every time, even though its value never changes. So since I mentioned that the process function would need to be optimized, so we will try and pull this out and pre-calculate the value. Now, the place where it can be pulled out to is where the frequency of it, essentially the frequency of it, is first available, which is in the constructor. We'll call this the offset, and I will initialize the value of offset to this value and reference it here. Cool, so that's our sine wave oscillator done. We'll create a new instance of this sine wave oscillator within our main function. We'll call the instance sine oscillator. And we'll initialize this object with a frequency of 440 Hz, which is A4, and an amplitude of 0.5. So we have a sine oscillator object, and we want to generate all the samples of this sine wave. So to do that, we need to put it in a loop of some sort. So I'll create a simple for loop for this. And I would have to iterate over the sample rate. So we would need to generate 44,100 samples to get a 1 second sine wave. So we can loop over the sample rate. Now, if you want to get more than 1 second of audio, then we can multiply this the sample rate by some duration. So let's say we want a duration of 2 seconds. We can iterate this loop over sample rate times the duration. Now within this loop, we will call the process method of the sine wave oscillator. Great. Now we need to write this into some sort of file. We'll make use of WAV streams or output file streams for this. And I'll name this file handle as audio file. Now the WAV stream is available and it's defined within the fstream header. So we'll include that here. We also need to scope the WAV stream to the standard namespace. But since this is a simple example, I'm going to use the namespace std throughout the file. So let's open this file. I'm going to call the file as waveform. I'm going to open it in the default output mode. The file named waveform doesn't really need to exist anywhere on the disk. If the program can't find the file, it'll just create one for us. Now what we want to do is just write the contents of the sine wave into the file just as a textual form, just to see what kind of values we are producing. So we can just write the floating point values that are generated from the sine wave oscillator directly into the file. I'll make use of the insertion operator here and we'll enter it line by line. Let's always remember to close the file once we're done operating on it. Let's run the program and see what we get. To run the program, I'll just call the g++ command on the file that we're writing, and this should compile us this should compile the file and should generate an executable for us. a.exe is the executable, and to run that, just call the executable. We're not writing anything to the console, so the program finishes execution and returns the control back to the terminal. So if you look at the contents of the directory again, we should find a file called waveform. Let's just open it. Now this file starts from 0, it goes all the way to 0.5, around 0.5. It drops back down to 0 and goes into the negative and bottoms out at around negative 0.5. And the whole thing repeats itself since it's a periodic function. And in the end, we should end up getting 88,200 distinct samples. But obviously, this is just textual data. To play back the audio, we need to write this as binary. So we'll go over here and we will change the mode of the file to binary. Another thing we need to do is to constrain the sample value to an integer. At the moment, the process method returns a floating point number between -1 and 1. This is a 32-bit floating point number. We had discussed quantization and bit depth previously, and you can check these videos out if you haven't already. Essentially, what we need to do is to truncate the word length to either 16 bits or 24-bit integer format, because most commercial audio is stored in that format. In my operating system, the size of the integer is 32 bits or 4 bytes in length. You can check this by outputting the result of the size of function into the console. As we can see, both the floating point number and the integer data formats are both 4 bytes in length. Let's choose to truncate the word length to 16 bits instead. In the end, our audio file would contain 16-bit audio sampled at 44.1 kilohertz. So that's basically CD quality music. With a resolution of 16, you can store, let me bring out my handy calculator, you can store 2 to the power 16 distinct values. This is unsigned 16 bits, meaning all values are positive, as we store from 0 all the way up to 65,535. Audio samples, on the other hand, are stored with a resting position or an equilibrium of 0 and can swing from positive to negative. For this, we need to use a signed 16-bit integer, where one of the bits is used to store the sign of the value, either plus or minus. So naturally, the range changes from negative 32,768 to 32,767, which is essentially 2 to the power of 15 minus 1. I'm going to get rid of the console logs here. We need to do a couple of things. Firstly, we'll need to establish the bit depth. I'm going to create another global variable here for storing the bit depth. And assign that to 16. And now we need to take the value from the process method, which has a range from -1 to 1, and convert it into a new range. Firstly, let's collect this as a floating point number. And then we can scale this up. Sample times, well, the highest number that we can have theoretically for 16-bit audio is 32,767. But let's calculate that programmatically. That's essentially 2 to the power of bit depth minus 1, the whole minus 1. And we can pull this out into another variable called max amplitude. I'm going to reference that here. This will have to be our integer sample, but obviously it's still floating point number so far. So for this, we need to cast this number into an integer. Again, as I mentioned earlier, this integer sample is still 4 bytes long, so we need to truncate that into 16-bit integers. We can do this while storing the data in the file. Instead of using the normal method, which is the insertion operator, to store the integer sample, we will make use of a more verbose method. We can make use of the write function defined within the oStream class, which accepts a pointer to a constant character, and the stream size, which is essentially the word length. We need to convert this integer sample into a character pointer. That's not very convenient, but we can make use of a reinterpret cast to do this. Be careful though, because there's no type of type checking that's involved when reinterpreting the cast. You should always know what the underlying data structure is before doing this. Over here, I've exposed the address of the integer sample. That's 4 bytes in length. A character in C++ is always 1 byte long, and we're extracting the first 2 bytes from this address, which will contain the entire sample value. Let's run this program now and see what we get. This is proper binary information now that our text file can't really read. But we won't really be able to rename this file to a .wav and expect it to work. That's because we haven't written any sort of metadata into the file. But there is a way to read the contents of this file and interpret it as audio. I'll go to Audacity, go to File, Import, Raw Data. And I'll select the file that we just generated. Now Audacity is asking me how I want the raw data to be interpreted as. We know how we've created the samples, but Audacity doesn't. So we need to give it that information. First one is the encoding, and it's 16-bit PCM that we've used. So choose that. We leave the byte ordering as little endian because that's the default byte ordering in Windows operating systems. And the channel count is 1. Start from the 0th byte. We'll import 100% of the audio, and we'll infer the samples as being generated with a sample rate of 44,100. If I zoom in, you can see that a sine wave is quite decently well sampled, and everything's as expected. It's 2 seconds in duration, and the amplitude of it is 0.5. Now we add the metadata, the relevant information to make this into a WAV file. It took us this long to get to the heart of what this video is supposed to be. Anyway, a WAV file format, as you may already know, is used for storing digital audio data. Most of the time, we store uncompressed PCM data in it. Well, this document here, I'll put the link in the description, explains how the WAV file is structured. I'll give you a very brief rundown here and we can get started. A WAV file is made up of chunks. You can think about a chunk as a grouping of relevant data. A chunk has an ID associated with it, but you can't use any value of your own. It has to be a recognized ID. Some of the valid, acceptable IDs are documented in this list. Right after that, it has a total size, which represents the size of the entire data within the chunk. After that comes the data actually associated with the chunk. How the data is formatted within the chunk depends wholly on the type of the chunk that you're using or the ID of the chunk that you're dealing with. The simplest WAV file, the one that we're going to be creating today, must have at least 3 different kinds of chunks. The first one is the format chunk. This chunk is responsible for holding all the relevant information describing how the audio is saved and how to play the audio back. Information like the compression scheme, the number of channels, sample rate, bit rate, and stuff like that. The second chunk is the data chunk. This will by far be the largest chunk in the file. This will contain the entirety of our audio data. Whatever sample data we've generated using the program so far will go into this chunk. Lastly, we have a chunk that encapsulates the 2 others that we've just talked about. This is the header chunk, the overarching chunk which contains other sub-chunks essentially. The ID of this one is RIFF, R-I-F-F, all caps. RIFF stands for Resource Interchange File Format, which is a generic file container format based on the concept of chunks. Similar to the others, it has a size field, which is essentially the size of the entire file, minus the bytes required to store the ID and the size field itself. And one last thing we need to write is the characters WAV. into the data section of this header file, which represents a WAV file. Well, we'll come back to this document in a while, but let's get started. Firstly, I'll modify this for the name of the file to also contain the extension of .wav. Now we start constructing the WAV file. The first thing that goes into the WAV file before anything else will be the header chunk. We can rely on the insertion operator here to write the first bit of data, which is ref. We can do this because the string that we're using is a character array. So each character will take up exactly 1 byte. So that'll be 4 bytes of data. Next, we need to write the size of the file. But the problem is, we don't know what the size of the file is yet. So I'll put a placeholder here. Why did I put 4 hyphens here? Well, the hyphens really don't matter. You can put anything you want here as a placeholder. But the document clearly states that the size of the header chunk is 4 bytes in length. Well, the document also gives us an idea of the different sizes of different fields that we may encounter. Next, we write the characters wave. That's the header chunk done. Now we move on to the format chunk. The ID of the format chunk is fmt. I'll put that in there. But there's a problem here. fmt is just 3 characters long. And the size of the ID field here clearly states that it's 4. But if you look closely though, there are 4 characters here. The last one is an empty character, a space or a null character. So let's not forget to include that in our program. Next, we need to write the size of the format chunk. Well, do we know this? Now let's look at the document. It says that the chunk data size is 16 plus extra format bytes. We'll skip the extra format bytes and we won't write these to the file. But the 16 is basically derived by adding up the sizes of the ones that we do need to write. So let's put 16 into the file. But again, we can't really write 16 directly. I mean, we can, but it's not a great idea to do so, because we need to explicitly state that the value 16 should be stored in exactly 4 bytes within the file. So similar to what we did here, where we have stated that the integer samples should be written to the file in 2 bytes, we can create a quick convenience method to write different sized attributes at different lengths. I'm going to call this write to file. I'll accept a file handle, and this will be a reference to a file handle because I don't need a copy of it. I'll accept the value in integers and the size. Pretty much what we did here, we'll copy that, which is we just need to write to the file, and we'll reinterpret the cast of the integer to a constant character pointer. The size of the value that we've provided. We'll reference this everywhere else in our program. Similarly, we'll write the size of the format chunk as 16 bytes. And the size of the format chunk is stored in 4 bytes in the file. And now for the actual metadata. The first one is the compression code, and it's represented by 2 bytes of data. There's a set of predefined values that are supported, and this table shows that. Most of the time, we'd want to use the compression code number 1. This represents uncompressed PCM data. PCM is pulse code modulation. The data that we've previously written to the file is PCM encoded, even though it wasn't all that obvious. It's a fancy name for a simple encoding mechanism. I've made a video on pulse code modulation, and you can check it out here if you want to. So we'll put 1 as the value of pulse of our compression code within the file. Next, we have 2 bytes of the number of channels. In our case, the number of channels is 1, so we'll write that in. Next, we have the sample rate, which is 4 bytes long. In our case, that's 44,100. So put that in. Now there's a limit defined for each of these fields. There's only a certain range of values that it can hold. So the highest sample rate we can sample at is essentially 2 to the power of 32. So this is the highest sample rate we can have, which is kilo mega giga. That's around 4.3 gigahertz, which is ludicrously high. So we can be assured over time that the size limitation won't hamper the wave format. But there is a field here that is sort of limiting. Can you spot it? On this one here, the size of the file in the header chunk. The size of the entire file can only be represented in 4 bytes of data, which is pretty much the same as this. So that's around a little more than 4 gigabytes of data. That's the limit to the WAV file, which in today's standards isn't really enough. But sure, 4 GB is quite enough if you're storing CD quality music. If you're storing audio at 44.1 kilohertz with a resolution of 16 bits, and if you're storing stereo, you can store around 6.5 hours of music. But if you're using really high resolution and oversampling it to 192 kilohertz with multiple channels of audio, it might not be enough. On that disappointing limitation, let's move on. The next one is average bytes per second. This is essentially bit rate, but they're asking for byte rate instead. Bit rate is quite simply calculated as the sample rate times the bit depth times the number of channels, which is 1 in our case. And this would be our bit rate. But they're asking for a byte rate, which is just calculated by a division of 8. Next, we have something called Blockline, which is 2 bytes long. This is a weird one. It's the number of bytes per sample size is what the document tells us. The Blockline field is used to determine how many bytes need to be available for a playback device of some sort at any point in time. So at any given point of time, there needs to be one sample of audio of all the channels available to the playback device. In our example, 16 bits, which represent 2 bytes, determine a single sample. And since we have a single channel, the Blockline field should just be populated with 2 in our case. So let's write that. And finally, we have significant bits per sample. This is just a fancy way of saying bit depth. So we'll just put the bit depth in there. This value here can actually be calculated as bit depth divided by 8. So that's the format chunk done. And we have one more chunk to go. This would be the data chunk. Similar to what we did earlier, we need the ID field, which is data, and we need the size of the entire audio data, which we don't know yet. So we'll pretty much do exactly what we did earlier. We'll put a placeholder there. Now for the actual data. Well, that part is done. We've finished that already by generating the sine samples and writing it to a file. So the last few things that we need to do to clean up and do some housekeeping is to fill up these 2 fields here that we have put placeholders on. How do we do that? Well, we can seek to a particular place in the audio file. We can use a method called seekp on the audio file, which will let us seek to a certain position within the file. But how do we know which position to go to? We need to set a marker of some sort, a variable to keep track of a particular position we need to seek to. We can find the entire size of the audio data if we knew the position over here before writing the audio data, and if we knew the position over here after writing the audio data. Subtracting the 2 would just give us the length of the audio data. Another way you could have done it is to keep a counter within the loop and just increment the counter over time, but we'll go with a former approach. To record the position, I'm going to use a method called tellp on the audio file, which is just the most weirdly named method. This will return the current position of the pointer within the stream. And we can collect it as an integer value. I'll call it pre-audio position. Similarly, I'll record the post-audio position here. You don't need to worry about managing this pointer. Every time we write to a file, the output stream is responsible for moving the pointer forward as well. Now we've got the markers set up, we can seek to this position in the file. So this position is basically 4 bytes behind the pre-audio position. So if we seek to pre-audio position and offset that by 4 bytes, we should be over here in the file. All we need to do is write the size of the file. The size of the file is essentially the post position minus the pre position. That's 4 bytes in length. And lastly, we have to seek to this position in the file and write the size of the file. We can use another variant of the seek method, which will let us put an offset of 4 from the beginning of the file. Now, the size of the entire file is essentially the post-audio position, because beyond this point in the file, we haven't written any new data. But as we discussed earlier, the size of the header chunk is basically the entire size of the file minus the size of the 8 bytes required to store the ID and the size of the header file itself. And we are done. If we've written everything correctly, this should generate a WAV file for us. And we should be in a position to play it back in any audio device. That is not right. There's just some audio there, but the duration is 4 seconds and it's playing much lower in pitch. So let's see what the problem is. Right, so it took a while, but over here the integer sample should actually be 2 bytes in size. Wow, that's a bummer. But let's try to run that again. There we go. That works. I hope you found that useful and it demystified and hopefully opened up the black box that is containers and file formats. But in any real world scenario, when you're generating audio files that need to be played back, you wouldn't want to do all of this low level plumbing yourself. You would much rather rely on a third-party library like libsoundfile to do this for you. That's because there are a lot of nuanced conditions that you might have to handle that's not very obvious. But anyway, I'm planning to make a lot more of these audio programming tutorials. So if you do want to check out more, do consider subscribing. Thank you very much for watching. See you in the next one.